Hi my dear friends, welcome back to our YouTube channel. This is ADC Max. The first basic type problem in the one-dimensional heat flow equation. See the question, solve dou u by dou t is equal to alpha square into dou square u by dou x square. So this is the one-dimensional heat flow equation, isn't it right? Alpha square is the diffusivity of substance, that is k by rho into c. When I solve this equation, I am getting u of x comma t. That is the required temperature distribution. Now, what is the given boundary conditions? You see that there are u of 0 comma t is equal to u of l comma t equal to 0. That means that there is a bar of length x is equal to 0 and x is equal to l. At these two sides, the temperature is 0 degrees Celsius. And the third one is when time t equal to 0, initially the initial temperature distribution is given x in 0 to L by 2, L minus x in L by 2L. So what will be the solution when I solve this one-dimensional heat flow equation? You see, already we know that the boundary conditions, what are the boundary conditions? The boundary conditions are already given here. What are they? This one, the first one, when x equal to 0, for all the time t, it is the temperature is 0, right? When x is equal to L, in the second end, u of L comma t, once again the temperature is 0 for all the time t equal to 0. And the third boundary condition is initial temperature distribution t equal to 0, it is x in between the interval 0 to L by 2. L minus x in the interval L by 2 to L, right? As what we know, that the one-dimensional heat flow equation is, what is one-dimensional heat flow equation? It is given that dou u by dou t is equal to alpha square into dou squared by dou x squared. So this is the given question, right? I want to solve this equation, where what is alpha squared represents? Is k by rho into c is called the diffusivity of substance. And already we know, what we know? The correct solution by using the method of separation and variable technique, we found that the correct solution for one which satisfies our boundary conditions, is given by u of x comma t is equal to a cos px plus b sin px into e to the power minus alpha squared p squared t. So this is my equation number 3. So let us apply the condition number 1, 2, 3 one by one. We will get the required temperature distribution. Let us see that. Let us using the condition number 1 in the equation number 2, by putting x equal to 0, we get. By putting x equal to 0, cos 0, 1, sin 0, 0. So into e to the power minus alpha squared p squared t is equal to, what is the temperature at the left end? 0 only. So it means that the product of these two terms is equal to 0. So either a equal to 0 or e power minus alpha squared p squared t is equal to 0. But e to the power minus alpha squared p squared t not equal to 0 because of, what is the minimum value for t? Is 0. Even though when we substitute for the minimum value for t 0, we get e power minus 0. What's e power minus 0 value? Only 1. So it is guaranteed that this is not equal to 0. So hence, which one is 0? A equal to 0. Let us substitute a equal to 0 in the equation number 2. We have the updated correct solution. U of x comma t is equal to b sin px into e to the power minus alpha squared p squared t. So this is my equation number 3. So once after applying the first boundary condition, I found that a equal to 0. Now can we use the second boundary condition? What is second boundary condition? When x is equal to L. When x is equal to L. So when x is equal to L, what happened? So when x is equal to L, let us substitute x is equal to L. When I substitute x is equal to L. So using condition number 2 in number 3, by putting x is equal to L, we get x is equal to L. The left hand side B sine x is equal to L. PL e power minus alpha squared p squared t is equal to, what is the temperature at the right end when x equal to L? 0. It means that either B equal to 0 or sine PL equal to 0 or e power minus alpha squared p squared t equal to 0. You see, in the first condition, I found that A equal to 0, isn't it? Isn't it? Now, if B is also 0, what happened? 0 and anything becomes 0. So, we get a trivial solution. So that B is not equal to 0. So, B not equal to 0. If B equal to 0, already what 0? A is 0. So, we will get a trivial solution. So, we will get a trivial solution. Because both the constants are 0, they ultimately get 0. But it is contradiction to the third boundary condition. What's the third boundary condition? It has some x in 0 to L by 2 and L minus x in L by 3. So, it is a contradiction to the given data. So, B not equal to 0. What about this one? E power minus alpha squared p squared t, it is also not equal to 0. Since the minimum value for t is 0, e power minus 0 is 1. E power minus 0 is 1. So, which one is 0 finally? Sine PL equal to 0. So, what are the values of sine under 0? It is the multiples of pi only. So, sine PL equal to 0 is equal to sine n pi. So, by this way, by comparing on both these sides, we get PL equal to n pi. N is a positive integer, pi is the constant, L is the length of the bar. So, the only unknown is P here. So, P is equal to n pi by L. So, let us substitute P equal to n pi by L in this equation number 3. We get the latest, the revised solution. P equal to n pi by L. So, n b into sin n pi x by L e to the power minus alpha squared. What's the P value here? N pi by L. So, n squared pi squared L squared into T. What is the B? So, B is the only arbitrary constant. If I substitute B equal to 0, sorry, I can't apply B equal to 0 because when B equal to 0, already A equal to 0, we get a trivial solution. B not equal to 0. So, B is equal to 1, we get one solution. B equal to 2, I get the second solution. B equal to 3, I get the third one. So, by assigning the different values for B, the arbitrary constant B, it will generate an infinite number of possible solutions. Among the infinite number of possible solutions, let us collect the maximum feasible solution. Let us get the most general solution. So, what is the most general solution? So, let us get the most general solution. Hence, the most general solution for the given one-dimensional heat flow equation is u of x comma t is equal to, by summing up all possible values of n, we get bn sin n pi x by L into e to the power minus alpha squared n squared pi squared t by L squared. So, this is my required temperature distribution function of the one-dimensional heat flow equation star equation. So, still I need to find out this constant Bn. So, how to get this constant? Still I have the third boundary condition. What is the third boundary condition? Initially time t equal to 0. So, at x equal to 0, we get a equal to 0. At x equal to L, we get p equal to n pi by L. Now, when t equal to 0, we get the Bn value. So, let us use the condition number 3 now. So, finally, using the condition number 3 in the MGS star equation, by putting t is equal to 0, we get. So, by putting t equal to 0 in this equation star, we get e power minus 0. So, e power minus 0, 1. So, the left hand side is sigma n equal to 1 to infinity, capital Bn into sin n pi x by L into the power minus 0 is equal to x n 0 less than x less than L by 2, L minus x n L by 2 less than x less than L. So, let us determine this Bn value by expanding the left hand side as the affine sine series. Okay. So, how to expand the left hand side as affine sine series? Let us see that. Let us see. because of the left hand side is sine n pi x by L. So this is looks like the half range sine series concept. This was already we have discussed many times frequently in the one-dimensional heat flow equation as well as the wave equation. So can we expand the left hand side is already there as a half range sine series model Bn sin n pi x by L. Now let us abbreviate the right hand side into the half range sine series. It is small bn into sin n pi x by L. Let us comparing or equating like coefficients on both sides. This is a similar way. So I found that bn equal to small bn. So what's the formula for bn? Yeah. So bn is equal to small bn is equal to 2 by L integral 0 to L f of x sin n pi x by L dx. This is the formula for the bn. Now in this function, this is the f of x. It can be divided into two subintervals. One from 0 to L by 2. It is x. The second half, it is L by 2 to L. In the second half, it is L by 2 to L. L minus x sin n pi x by L dx. Right, sir? It's clear? So we can divide this into two separate integrals and apply the Bernoulli formula. You will get the answer. So let us see that 2 by L is taken outside. I go for the first integration for this term. X sin becomes minus cos n pi x by L by n pi by L minus for the formula minus Bernoulli's formula. X difference with respect to x we get 1 and let us integrate this one we get minus sin n pi x by L by n pi by L to the whole square. What about the next term? Next term is 0. So let us close the bracket. Then the limit for x is equal to 0 to L by 2. Plus the second integration. This time L by L minus x is the u. So L minus x sin becomes minus cos n pi x by L by n pi by L and minus by the formula minus L minus x difference with respect to x we get minus 1. Then integrate this we get minus retained the minus sin n pi x by L by n pi by L to the whole square. So let us close once again this one. For the lower limit is L by 2, upper limit is L. Now substitute the limit, you will get the very interesting terms. When I substitute x equal to L by 2 here, so we get this L by 2, right? And minus sign, so minus coming back front side. The reciprocal is L by n pi. Putting x equal to L by 2, we get this cos n pi by 2. After cancelling the L, this minus minus plus L squared by n squared pi squared into, by putting x equal to L by 2, we get sin n pi by 2. By putting x equal to 0, 0 nothing 0, sin 0 is 0. So the lower limit is completely 0, vanishes. Right? The second term now. Plus, by putting x equal to L here, L minus L 0, 0 nothing 0. By putting x equal to L, sin n pi is 0. So that is also 0. So for the first term, lower limit is 0. For the second integral part, the upper limit is 0. So upper limit is 0 minus the lower limit. X equal to L by 2. L minus L by 2 is L by 2. Right? This minus sign is minus sign. This is a reciprocal L by n pi. And cos n pi by 2. Cos n pi by 2 minus, minus minus plus, plus and minus is minus. The reciprocal of the denominator, this is L squared by n squared pi squared into sin n pi by 2. So let us simplify this. I think so. What I think this is the minus sign, this is the minus plus sign, it will cancel. What about this one? Minus or minus becomes plus. So this is once again L squared by n squared pi squared. This is also L squared by n squared pi squared. So finally I found that capital Bn is equal to small bn is equal to 2 by L is front side. After cancellation of 1 we get it is 2L by n squared pi squared into sin n pi by 2. I think so it is 2 into 2, 4 only because of 1 plus 1, 2 times L squared by n squared pi squared. So 2 to 4 L squared by n squared pi squared. But after cancellation of 1 L we get it is 4L by n squared pi squared sin n pi by 2. So this is my Bn value. Let us substitute this in this NGS. We get the required most general solution and the required temperature distribution of the given function. So u of x comma t is equal to sigma n is equal to 1 to infinity 4L by n squared pi squared sine n pi by 2. So this is to complete the constant. So complete the constant, and sine n pi x by l into e to the power minus n squared pi squared l squared into t. So sine of n pi x by l into e power minus alpha squared n squared pi squared t by l squared is the required temperature distribution. Is the required temperature distribution function. So this is the way to get the given boundary conditions from the one-dimensional wave equation. So I hope everyone is enjoying this problem. So signing off. This is your ADC. Please kindly subscribe our YouTube channel, ADC Max. Thank you so much for watching our YouTube channel.